everyone. We're team number 7 and we're going to be presenting to you about power transmission system design. My name is Reyes. I am with my partners here, Jorge and Ramon Garo. Our problem definition is that we have to design a power transmission system. It must have a horsepower of 4.0. It must have an input and output speed of 800 RPM and 40 RPM. And also, it must have an in and out direction. It has to be the same direction.
Okay, the gearbox or transmission, that's most common in automotive application. First of all, the gearbox, what is gearbox? Gearbox adapt the output of internal combustion engine to the wheel drive, which is the engine. Such engine requires so high revolution, so the gearbox reduce the revolution to lower revolution, which is the wheel revolutions. And one of the early transmission system would be the windmill, the steam engine, and pumping.
We considered several different gear types for this project, including spur gears, which are the most common and the simplest gears to design, helical gears, which have very high precision but are also more costly due to the nature of the manufacture of their angled teeth, herringbone gears, which have the same advantage of helical gears, where the precision is very high, but they lack the disadvantage of needing of generating a thrust force and thus needing tapered bearings. And finally, planetary gears, which are more complicated in design but have many of the same advantages as spur gears and are able to reduce the weight and volume of a gearbox design.
This is our final conceptual design. It consists of 3 shafts. We have one transmission shaft, which is 12-inch long, and then we have a 2 input and output shaft, and it consists of 2 small gear and 2 larger gears.
Here, we can actually see the different assembly animation. You can actually see the gears moving correctly. The mating is successful, so that means our design was pretty much successful and accurate as much SolidWorks can say. The interference was very minimal. Also, in the next slide, we can see the exploded view. So in other words, if we were supposed to take this to a manufacturer, they will know how to put it back together. Another thing to consider is the BOM. Here we actually listed every single item we needed to construct this gear design or this power transmission design. We had a special casing just for this. Of course, we used some of the gears that came from the catalog, such as Boston gears. The bearings came from Tincam, and the shafts were like custom made.
On the following slides, we have excerpts of our calculations for the structural designs. Notably up top, we see that the gear train value desired was 1 to 20, which is too high to be achieved with a single stage, thus requiring the 2-stage gear reduction that Jorge mentioned earlier. Finally, with our final choice of gears, we had a 1 to 20.25, which results in only a 1.24 difference from the actual desired speed at the end. Our diametral pitch was 16th per inch, and as we see here, the respective pitch diameters of the 2 gears. The 2 small gears are 2.67 and the larger gears are 12 inches.
According to our calculation, we select the Boston gear catalog, the gear 2 and 4 to be YJ16 10004, and gear 3 and 5 to be the YJ72B 10724. Why we choose these gears? First of all, the most critical gear would be the inner gear, which is the small pinion. That would be the gear 2, and then that's the one that you see more stress concentration. And this is the bending wear, gear number 4 that I was talking about.
Finally, we have here the radial forces of the normal forces for the 2 critical bearings, which are bearings A and B, which are the ones that support the transition shaft. You see there that the loads are 141.4 pound force and 331.7 respectively. Our combined, following on the bottom, you see the combined shear moments and finally the maximum torque diagrams for the transition shaft, which is the shaft connecting gears 3 and 4.
The cost estimate for this entire project, it rounded up to be $1,179 with 66 cents. The most expensive component for this was, of course, the largest spur gear that we used with a total amount of $729.48. That's because we used 2 of them.
The maintenance, this is one of the critical once you set up the gears. You see the oil check. You need to do the constant oil check in order to assure the gear is perfectly lubricated. If it's not lubricated, the gear might fail or overheat. And of course, in the different type of lubrication, if lubrication is not that well, then the gear will have a metal-to-metal contact, which is end up causing the scoring and gearlings. And of course, if the foreign material is present on the lubrication, then you have abrasive wears. And these are the applications that we came up with, the one on the garage door and auger. Here's a basic sample. Here's a sample animation using the garage door. That's where you see the motor, and then that's where you see the output.
Finally, in conclusion, what we have here is our gearbox was successfully able to transform the power to drastically increase the torque while reducing the speed to almost exactly the desired speed. As mentioned earlier, the true output, the actual output, is 1.3% different from the desired output of 40 RPMs. It's a 39.506, which is a very small difference from the 40. Finally, we use spur gears because it is possible to achieve high precision with spur gears as long as it's designed properly, and the extremely large variety of spur gears makes for a lot of choices, which allowed us to achieve that small 1.3 difference. Finally, looking forward, if we were to redesign this gearbox, we'd probably consider using a planetary gearbox as opposed to a parallel shaft gearbox, and that would allow us to drastically reduce the weight and the overall volume of the gearbox while maintaining the robustness and the desired gear ratio. Thank you.
Thank you.
Thank you.